Hello and welcome to this workshop on KSP and solubility products. My name is Matthew Woods. I'm Assistant Director of the Academic Support Center at the College of St. Rose. And we are going to begin in a moment. First, I just want to remind you that you should have printed out the student copy available on the St. Rose website. And you should follow along in that and fill in the blanks as they come. During this presentation, there will be chances for you to do the workout on your own. At those times, I ask you to please pause the video, do the workout, and then resume playing once you've found an answer. Now, I always like to begin some of these that are intense, like the solubility products can be, by letting you know what items you're going to need for these problems. You'll need a scientific calculator that can handle scientific notation roots other than square roots, like cube roots and fourth roots. A pencil. You can use pen, that's fine, but I recommend pencil just so you can erase if you make a mistake. Paper, obviously, if you have something to write on. A periodic table, and the chart for different polyatomic ions. So the ones that I would recommend knowing are hydroxide, OH, sulfate, SO4, carbonate, CO3, and phosphate, PO4. All right, so if you know those, you'll probably be fine for any of these KSP problems. All right, and before we begin even more, these are three terms that you need to know, especially the first two here. Solubility is in grams per liter, different than molar solubility, which is moles per liter. So solubility is in grams, molar solubility is in moles per liter. And the one that you use for KSP is molar solubility. All right, so solubility is grams, molar solubility is moles, and KSP is based off of molar solubility. All right, so let's begin. This is an example problem. The one-to-one up here is basically saying that you have one positive ion, one cation, to every one anion, every one negative ion. So what is the molar solubility of BaSO4 in water at 25 C if the KSP is 1.5 times 10 to the minus 9? This capital E here means 10 times 10 to the, and this minus 9 is the power. So this is 1.5 times 10 to the minus 9. Just hard to type times 10 to the minus 9 on PowerPoint. So what do you have to do for these? First step, you have to write out the dissociation reaction of the salt here, BaSO4. And that looks like this. You've got BaSO4 goes 2 and back, Ba plus 2 plus SO4 minus 2. Next thing you have to do is create the ICE table. ICE is how I was taught when I was in high school and when I came here to College of St. Rose. It stands for Initial, Change, Equilibrium. And I'm sure you've seen something along those lines. It looks like this. So here's the initial, here's the change, and equilibrium, these are the concentrations. Notice that the BaSO4 has no values over here. That's because BaSO4 is a solid, and its concentration doesn't change at all. In fact, solids, we say, don't have a concentration. Then you just plug your values into KSP and solve. KSP is just like any other equilibrium constant. So it's concentration of the products over concentration of the reactants. Now the only difference, again, is that BaSO4 doesn't have a concentration, so KSP is just the product of the products. Kind of hard to say that, but multiply these two concentrations together. And here's what the work looks like. KSP equals concentration of barium plus 2 times the concentration of SO4 minus 2. There's the value of KSP taken right from the problem, equals S squared. I've got S times S, so that's going to be S squared. And the square root of that will just give me S. And here's the square root, 3.87 times 10 to the minus 5 molar. If at any time during the presentation you have questions, my email address is on the College of St. Rose website and will also be printed in the description for the video. All right, here's the first one that you're going to do on your own. Determine the molar solubility for iron carbonate, so that's iron 2 carbonate, FeCO3, if its KSP is 2.1 times 10 to the minus 11. So pause the video, do the workout, unpause when you have your answer. Did you get 4.58 times 10 to the minus 6 molar? If so, you got it right. If not, check your work. Here are the big steps out. You should have 2.1 times 10 to the minus 11 equals s squared, and you're just taking the square root of that. So now we're going to step it up a little bit. Instead of 1 to 1, we're going to have an uneven ratio. So what is the molar solubility for silver carbonate if its KSP is 8.1 times 10 to the minus 12? Now the thing you should notice here is that 2 on the silver. All right, it's not, silver's not a polyatomic ion, so that 2 is going to make a difference. And the process is the same, except Ag gains 2s. Not s, 2s. So when you substitute into KSP, it's going to be 2s squared. Remember, when you have the reaction out, it's always the coefficient becomes the power for the term in KSP. And when you do it, it should be 2s in parentheses squared, not 2s squared like this. At the end, you're going to do the cube root, not the square root. So this is what the work looks like. Concentration of Ag plus squared times CO3 minus 2. And 2s squared is 4s squared. That's 4s cubed. Notice how I didn't put the value of KSP in until I've got one term with s. You can have it in here and leave it all throughout. That's fine. I just like typing it in at the end. I mean, if you want to have it, write it here and write it here and write it here, you're more than welcome to. But I find this is easier. So then now it's just algebra. So you divide by 4 on each side to get this, and take the cube root, and there's your value of s. Remember, s is molar solubility, so that's why this is in molarity, moles per liter. Now you're going to try this one on your own. What's the molar solubility of lead 2 chloride if the KSP is 1.6 times 10 to the minus 5? Pause the video, do the work, unpause to get the answer. Did you get 7.44 times 10 to the minus 3 molar? It's still 4s cubed because it's still a 2 to 1 ratio in some respects. I've got 2 CLs for every 1 PB. So it's still going to be 4s cubed that I'm plugging into KSP. And the cube root of this value here, 7.44 times 10 to the minus 3. What else could you be asked for in a problem like this? Molar solubility of a compound is always S. So the molar solubility of PbCl2 is 7.44 times 10 to the minus 3. That's just pretty much the concentration of PbCl2. That's basically the max concentration you can get in a saturated solution. Molar solubility of an ion is what you plug into KSP. So if we go back to here again, S, in this case, would be lead, and this is the concentration of lead ions in solution. 2 times this would give you the concentration of Cl ions in solution. All right, so S, 2S, 3S, those are the solubility concentrations of an ion. And when you're looking for the ion concentration, you never square or cube it. You only do that when you're going to KSP. Solubility needs to be converted to grams. So remember, solubility, not molar solubility. So you multiply the molar solubility by the molecular weight. And you could be asked to find a KSP if you were given the solubilities. And yes, that could be either molar or gram per liter. So you're going to try this one. The KSP of strontium hydroxide is 3.2 times 10 to the minus 4. Determine the solubility of the compound and the molar solubility of OH minus. Pause the video, do the work, unpause to get the answer. Did you get the molar solubility? The solubility of the compound is 5.24 times 10, or just 5.24 grams per liter. So I've got times 10 on the mind. And the concentration of the OH is 8.6 times 10 to the minus 2 molar. Remember, if at any time you have a question, please just feel free to send me an email, and in the subject heading, put the name of the workshop. Now we're going to talk about the common ion effect, and that's the last big topic for the workshop today. And sometimes you start in a solution with one of the two ions from your salt present. So instead of pure water, you start in a solution. If that happens, solubility will go down. If it goes up, you screwed up. Go back and do it again. Suppose that instead of water, a solution of 0.1 molar Na2SO4 was used for dissolving that solution of BaSO4 from slide 4. What's the new solubility? And yes, that should be molar solubility. I apologize about that. So we're going to do this one a little bit together. And you'll notice the process is the same, but we're going to change it slightly, just one little change. And that is the SO4 minus 2 now has a starting concentration of 0.1. So there's my reaction, the same as before. Now here's the ice table. See, there's the difference. At equilibrium, I've got 0.1 plus S instead of just S for that SO4. Why not the Ba? Because the Ba is not in solution. The Ba is still just going to be S. KSP doesn't change. KSP is the same no matter if you're in water or a solution. And if the KSP is more than 3 orders of magnitude away from the solution, you can drop the plus S. And that remains true even if you have to square the term. So in this case, the KSP, remember, is 1.5 times 10 to the minus 9. Times 10 to the minus 9 is a lot lower than 0.1. So 3 orders of magnitude means 1,000 times less. So this is much more than that, so we can drop this plus S when you plug in the KSP. So here's the workout. KSP equals S times 0.1 plus S. Here it is. I just dropped that plus S term. Then divide by 0.1, and there's solubility, molar solubility. All right, we're going to do another one together because this one's kind of a big one. What's the molar solubility of Ca3PO42 in a solution of 0.5 molar Na3PO4? And the KSP for Ca3PO42 is 1.3 times 10 to the minus 32. So remember, the first thing you got to do is start with the reaction. So this is what it looks like here. The reason why I don't have this on every slide for the reactions is just I need to save some space. Here's my ice table. Calcium's going to gain 3S. Phosphate starts at 0.5 because that's the concentration from there. And that's going to gain 2S. Now here's the rest of the work shown out. It's 3S cubed times 0.5 plus 2S squared. So KSP is 1.3 times 10 to the minus 32. That's minuscule compared to the 0.5 molar. So I can drop that plus 2S. 0.5 squared is 0.25. 3S cubed is 27S cubed. Then the work from there is just algebra. And you should get 1.24 times 10 to the minus 11. All right, you're going to do this one on your own. What is the molar solubility of CuOH2 in a solution of 0.004 molar NaOH? The KSP for CuOH2 is 1.6 times 10 to the minus 19. Pause the video, do the work, then unpause for the answer. Did you get 1.0 times 10 to the minus 14? It's still going to be S times something squared, and I can drop that 2S because 0.004 is more than 3 orders of magnitude away from times 10 to the minus 19. All right, that's the end of the workshop. Thank you. If you have any questions, please feel free to email me at the email address that's provided. And have a good day.